All right, so we're going to be going over chapter 2, lesson 7, graphing inequalities. This is the last section in this chapter. So we're going to learn about graphing linear inequalities and then also graphing absolute value inequalities. So really the main vocabulary to keep in mind here is a boundary. So we'll talk about that in the lesson. So when graphing linear inequalities, it really resembles graphing linear equations, but with an inequality symbol instead of an equal symbol. So for example, if we were dealing with y is less than or equal to x plus 1, that is going to be very similar to when we were graphing y equals 2x plus 1, right? They're both in slope-intercept form, slope, y-intercept. So we're going to treat them very, very similarly. So the graph of y equals 2x plus 1 separates the coordinate plane into two different regions. This line is known as a boundary for each region. The graph of the inequality, y is less than or equal to 2x plus 1, is the shaded region, right? And so basically every point in the shaded region of a graph satisfies the inequality, where if it's an equation, it's a solid line that shows you that those points are a solution. So here's an example of what the graph of a linear equation looks like, right? But the inequality would be all the data points that are on that line and anything in this area, because all of these x and y values are going to satisfy this inequality. Where for an equation, only the coordinate points on the line are going to satisfy the equation, right? But since this inequality has an equal sign, it can be equal to the line, right? So anything on the line, or anything less than, which would be anything below the line here. So anything going on forever below this boundary line here. So you can graph an inequality by following these steps. So step 1 would be to determine where the boundary line should be and whether it's solid or dashed. So as long as you can graph a line, you should be able to graph linear inequalities. Step 2, choose a point not on the boundary and test the inequality. So one of the things that will come up is a lot of times we'll test 0, 0, because it's really easy to substitute 0 in for x and y and see if that solution, if that works as a solution. The only time you cannot pick 0, 0 is if it's on the line, because the whole point of testing the coordinate is to see what side of the line you should be shading. Step 3, if a true inequality exists, then you would shade that region that contains that test point. If it's false, then you would shade the other region, because all the shaded area is just showing where your solutions occur. So let's look at an example. So when we're graphing 2x plus 3y is greater than 6, first thing we want to do is we would want to take that inequality and basically graph the boundary line, right? If we were to imagine it as an equation, what line would it make, right? So the first thing we can do is we can turn this standard form linear equation into slope-intercept form. And if you remember how to do that, you just solve for y, right? Subtract 2x on both sides and divide by 3. And so if I do that, I'd be left with this equation here, y equals negative 2/3 x plus 2. So now I know my slope of my boundary line has a slope of negative 2/3 and a y-intercept of positive 2. So it would look something like this, right? Y-intercept of positive 2, and I know that it goes down to over 3, down to over 3. Next step is we want to test a point now, because now we need to know what side of the line we should shade. So we would want to either, this is an example where we could use the point 0, 0 because it's not on the line. Again, you don't want to pick any point on the line. You want to pick a point on either side of the line. 0, 0 is just the easiest one as far as for computational reasons, right? So if I take my original inequality and I substitute the x and y value, right, 0, 0, I substitute them into their place, and then I can evaluate this inequality and see if this actually works as a solution. Well, I know 2 times 0 is 0, and 3 times 0 is 0. And then if I do 0 plus 0, that's also 0. So basically 0 is greater than 6, which we know is not true. 0 is not greater than 6. That makes a false statement. So therefore the point 0, 0 fails as a solution. So that tells me that none of the solution, or none of the points on this side of the line will be a solution. And all of the solutions occur on this side. So I would make a graph like this, right? My boundary line needs to be dashed because if you remember, it is a greater than symbol. It's not equal to. So none of my solutions can actually occur on this line. And since the point 0, 0 did not work as a solution, I have to shade everything above the line on the other side of the line. So this would be a graph for the linear inequality 2x plus 3y is greater than 6. So inequalities can also sometimes be used to model real world situations. So here we're going to talk about a business situation here. So it says a mail order company is hiring temporary employees to help in their packing and shipping departments during their peak season. So these are the different parts of the problem. So first we have to write an inequality to describe the number of employees that can be assigned to each department if the company has 20 temporary employees available. Next, we want to graph that inequality. And then finally, we will identify if the company can assign 8 employees to packing and 10 employees to shipping and see if that still works as a solution. So let's start with part A. So we're going to write an inequality based off the situation, right? So we're going to let P be the number of employees assigned to packing. We're going to let S be the number of employees assigned to shipping. And since the company can assign at most 20 employees total, because that's what they have available to them for the 2 departments, we're going to use less than or equal to, okay? So this would be my inequality. P plus S must be less than or equal to 20, right? The number of employees for packing plus the number of employees for shipping is at most 20, right? So those number of employees have to be less than or equal to 20. So there's one inequality that I could write for that. Now, part B is let's graph it, right? So if the inequality symbol was a less than or equal to, the graph of the equation is going to be solid, right? In the last example, it was dashed because it couldn't be equal to the line. Well, in this scenario, it can, so it will be solid. So P plus S equals 20 is going to be my boundary line. So in this scenario, it'd probably be really easy to find the X and Y intercepts, right? Plugging in 0 for each variable. And so that would give me this graph right here. The other thing you can do is you can solve. And remember, if it's not an X and Y variables, remember a lot of times it's an alphabetical order. So, but in this scenario, it's going to be really easy to find X-intercept of 20 and a Y-intercept of 20. So now we're going to go ahead and test. So I can test the point 0, 0 because it's not on the line. So if I test the point 0, 0 and it works, I would shade on this side of the line. If it was false, I would shade on this side of the line. So let's go ahead and do that. So here's my original inequality. I'm going to plug in 0 for each one of those. Clearly, 0 plus 0 is going to give me 0. And 0 is less than or equal to 20 is a true statement. So this point does work as a solution. So that means everything on this side of the line is going to be a solution, right? So since this is where the solutions are, that's the side I'm going to shade, and my graph would look something like this, right? Here's my line, my boundary line. It's solid because it can be less than or equal to. And I would shade everything on this side of the line because my test point 0, 0 was true. So everything on this side of the line would be true. If it was false, I would have shaded on the other side of the line. And it makes sense because basically any point that I would select on this graph is going to make my inequality true. So let's go ahead and use that information to help us answer C. So it says, can the company assign 8 employees to packing and 10 employees to shipping? Well, that would tell me that 8 employees to packing would be here, 10 employees to shipping would be here. So that means that would be a point located in that shaded region, which I know would be true. The other thing you could do is you could also test it out. You can plug 8 and 10 in for P and S respectively into the inequality, and it's going to end up giving you a true statement. So let's go ahead and talk about graphing absolute value inequalities. So we talked about linear inequalities. Now we're going to talk about absolute value inequalities. Well, graphing absolute value inequalities is going to be very similar to what we've just done with linear inequalities, right? First thing we're going to do is going to graph our boundary, and then we're going to test one of the areas and then shade. So let's look at it. So here is a inequality involving an absolute value, right? So y is less than the absolute value of x plus 1. So since the inequality symbol is going to be a less than symbol, it is going to have to end up being a dashed graph. And the graph is related to this equation here, y equals the absolute value of x plus 1. So again, absolute values, remember, make that V shape. It does get shifted up 1, right? And again, you can use Desmos to help you verify these in case you need some extra help. So this would be our graph of this equation here. And so now we have to go ahead and we have to test, right? Do I shade below or do I shade above? So I'm going to test the point 0, 0 because again, it's not on the actual line itself, right? Or the actual function here. It's not on that. So I'm going to test the point 0, 0 and see if it works. So I'm going to substitute it into the original inequality. And that's going to give me the absolute value of 0 plus 1 is going to be 0 plus 1, which is 1. So is 0 less than 1? The answer is true, right? This does make us true. It is part of the solution set. So since this is part of the solution, that means everything below the graph here is going to be part of the solution. So I would want to shade it. So I'm going to go ahead and shade that region. And my answer would look something like this, right? The absolute value inequality would be a shaded line, right? And then I would, a dashed line, and I would shade everything below it. Because remember, 0, 0 was part of the solution set. So that means everything below it will also be part of the solution set. So that's how you would graph an absolute value inequality. All right, thanks for watching. Remember to ask questions if you have any.